using this expression sigma t by epsilon t, where sigma t is a stress amplitude, epsilon t is a strain amplitude. And here phase angle, which is a lag between a stress and strain, is given by 360 into F into S, where F is the frequency of testing, S is the time lag between a stress and a strain. So, F is frequency of testing and S is a time lag between stress and strain. So, now here for a repeated loading, we calculate a modulus called a flexural beam stiffness and the phase angle using this equation. This flexural stiffness and the phase angle is further used in determining the fatigue life of a bituminous mixtures. So, now we know what is flexural stiffness, but if you see the evolution of a flexural stiffness, it exhibits a 3 phases. So, flexural stiffness as given in a y-axis will be a function of number of load applications. You can see a 3 phase, phase 1, phase 2 and phase 3. So, in the initial phase there is a drastic decrease in the flexural stiffness, and in the second phase the decrease in the value is uniform and it is gradual, and in the third phase again the flexural stiffness value decreases. So, we expect a decrease in the flexural stiffness as the damage accumulates. The initial phase is not due to a damage accumulation. This initial phase decrease in flexural stiffness may be attributed to a steric hardening of a sample or due to a initial temperature thermal changes that is happening due to a loading, due to a beam loadings. So, this ignoring this initial decrease in the flexural stiffness. Now, if you see phase 2, you have a gradual decrease. We say that this gradual decrease, a micro crack starts in this gradual decreasing phase, that is in phase 2, the micro crack starts forming. So, the micro cracks coalesces to form a macro crack when it moves from a phase 2 to a phase 3. So, we say this is the initiation mode and the crack propagation mode as a phase 3, and again it is a hypothesis. Initiation mode is at phase 2, it is hypothesized or it is assumed that in the phase 2 the micro crack starts forming, and in a phase 3 all this micro crack coalesces and the propagation of a crack occurs, and this due to that the stiffness reduces drastically. So, you can see a flexural stiffness calculated for a different strain levels for a, this is for a bituminous mixture prepared with Vg30 sample at 10 Hz frequency when tested at 10 Hz frequency and 20 degrees Celsius. So, the test was conducted at 200, 400, 500, 600 and 800 microstrain. So, you can see that the stiffness modulus decreases with the loading, and you have to note that this is a logarithmic scale. So, initially there is no much difference in stiffness observed when you test it at different strain level, but as the damage progresses, higher strain level, this 800 microstrain, if you see, the damage occurs or the modulus decreased at a faster rate when you test at higher strain level, and the rate was slower at a lower strain level. Say for example, comparing this 800 and the 200 microstrain. So, damage accumulates at a faster rate as the modulus decreases at a faster rate, 800 microstrain when compared to this 200 microstrain. So, this is how the flexural stiffness varies. So, the reduction in flexural stiffness depends on the strain we use. Again, the evolution of flexural stiffness also depends on the test temperature. Now, if you see test temperature at 0 degree and 20 degree. So, this is the test conducted without rest period on continuous loading at 0 degree, and this is a test conducted without rest period at 20 degree. So, 0 degree has a high flexural stiffness compared to 20 degree as expected, and again the rate of decrease is also not same, that you will observe when you plot a normalized plot. Normalized value, you can normalize the value and plot it and check whether how the rate of decrease in modulus occurs. So, when you compare again with rest and without rest, you can see this is at 20 degree Celsius with rest and this is without rest. So, when you compare a with rest and without rest data, you can see that rest period has improved the rate of decrease in stiffness modulus. So, now we have calculated the stiffness modulus for different load cycles. Now, we need to find out from the stiffness modulus value, we need to find out what is the fatigue life of a bituminous mixtures. There are various post-processing methods available to calculate the fatigue life of a bituminous mixtures. So, few of the post-processing method, but not limited to this, are listed here. It can be broadly classified under 2 groups, flexural stiffness, or even 3 groups. One is determining the fatigue life based on the flexural stiffness, determining the fatigue life based on the phase angle, and then determining the fatigue life based on the energy dissipations. So, we will see in detail how this post-processing methods are. So, fatigue life calculated based on the stiffness. So, then the AASHTO T32110, now we have 2014 revision. 2014 revision recommends a different method of fatigue life calculation. As per AASHTO T321 2010 and as per the EN standard, fatigue life is estimated using a stiffness value or a flexural stiffness value. It says that damage in a pavement occurs when the flexural stiffness falls less than 50% of the pavement. Identify a number of cycles corresponding to the 50% flexural stiffness. So, we should know what is an initial stiffness here. Initial stiffness, as you saw, there is a phase 1 progress. Just to avoid a phase 1 progress, initial stiffness as per AASHTO is taken as 50th cycle. Initial stiffness as per AASHTO is taken as 50th cycle and as per EN standard is taken as 100th cycle. So, initial cycle, as per initial cycle, pick the initial cycle, find out what is the number of cycle corresponding to the 50% of stiffness of initial cycle, and that number gives you the fatigue life of a bituminous mixtures. In case if you need to extrapolate the value, say for instance the initial stiffness here is 7000, 50% of initial stiffness, which is 3500, occurs somewhere here below. So, now it has that during testing the test was stopped below before it reached the initial before it reached the 50% stiffness. So, now in this case you can use a exponential fit and estimate the fatigue life corresponding to the initial corresponding to the x value here, or you need to find out what is x value for the corresponding y of 50% of initial stiffness, 50% of initial stiffness or a stiffness modulus at ith initial cycle. And ASTM D8237 recommends a normalized modulus for calculating the fatigue life. The normalized modulus is nothing but the normalized value of normalized value of stiffness modulus, where SI is measured at the initial cycle, that is at 50th cycle, and S naught is at the 50th cycle, which is at the initial cycle. SI is at the ith cycle. So, you normalize the value with respect to the initial stiffness. So, and multiply by the product of Ni by N0. If you do this, we call this as a normalized modulus. So, when you plot a normalized modulus as a function of number of cycles, the x scale here is n, you will get the normalized stiffness plot to be of this trend. Identify the peak point, and this peak point is assumed as a failure point. So, in case if you find it difficult to identify the peak point, you can fit a normalized modulus to the 6th order polynomial function and differentiate that 6th order polynomial function, and after differentiating find the number of cycle corresponding to the maximum function, you will get a value of n. You can also use a logistic equations to determine the fatigue life of bituminous mixtures. Now, if you see a normalized modulus curve, as per ASTM recommendations, the typical normalized modulus curve looks something like this, type 2 response. So, you have normalized modulus curve type 1, type 2, type 3, type 4 response. The typical ASTM code normalized modulus curve looks like this. It increases, reaches a peak value, then decreases. We will identify the point corresponding to the peak point as a fatigue failure point. Now, if you see a type 1 response, the test was terminated before it reaches the peak value. Type 3 response, it reached a peak value, but further there is no decrease in the normalized modulus value. In a type 4 response, not clear here which is the peak point. So, there is, even after attaining one specific, you have a localized peak and there is still increase in the modulus value. So, it is not clear how to determine the fatigue life of all these two conditions, but here for this conditions we can use a Weibull fit for determining the normalized modulus. So, ASTM says that ideally the test should be terminated sometimes or after the normalized beam stiffness and the product of normalized beam stiffness and normalized cycle peak value has the failure point, that is peak value, has been achieved on the graphical plot. If this is not achieved, you can use a Weibull distribution as described in this note. So, this generally occurs, Weibull distribution conditions fitting generally occurs when we test it at very low strain level. ASTM also gives the point when to stop testing. So, if you see that it is suggested that the test to be terminated after the flexural stiffness reduces 15% beyond the failure point. So, this is the conditions given for a termination of a test period. So, there is a small comparison between fatigue life obtained from a 50% stiffness and logistic model or using a Weibull distribution fit. Now, if you look into this first equations, SR equal to 0.5, this fatigue life is based on the 50% stiffness, initial stiffness. Now, if you see this maximum of S is based on the logistic fit, or sorry, based on the peak point of a normalized modulus plot, and the fit here is a logistic fit model. Here the second plot, again it shows that 50% modulus is here, the maximum point is here, this is SR into N, this is stiffness modulus, this is into N, same functions. Now, if you see a Weibull fit, so based on the Weibull fit, if you calculate, you can see that 50% stiffness and the maximum point occurs almost near, but if you do it based on the logistic equation, you can see a difference in the fit. So, it depends on what fitting equations we predict, the fatigue life also varies with the equations. So, this is a normalized modulus curve. Now, if you want to see a damage that occurs at the different stage of a normalized modulus, the damage can be seen by plotting a Lissajous plot. If for an undamaged sample, the Lissajous plot will be an elliptical, and for as the damage progresses, the Lissajous plot will disorient from an elliptical shape to a non-elliptical shape. So, now if you take a 3 or a 4 points, mark 4 points on the normalized modulus, one at the initial stage, next at the peak stage, and C and D at the nearing the end of the sample life. Now, if you see at A and B, the Lissajous plot, one is elliptical and other B is also nearing elliptical. At C and D, you can see the Lissajous plot to be a non-elliptical shape. So, this non-elliptical Lissajous plot can be used as a factor to identify the damage, or it also shows the damage in this extent of damage in the sample. The next method of identifying or determining the fatigue life of a bituminous mixture is using a phase angle value. So, a phase angle value, as the damage progresses, phase angle is plotted as a function of number of cycles. Now, at the point of damage, at the extreme point of its damage, you can see the decrease in the sharp decrease in the phase angle, and this is taken as a fatigue life of a bituminous mixtures. The next approach of determining the fatigue life is using an energy dissipation value. Dissipated energy, which in a short form can be noted as DE. So, this dissipated energy, generally we find it using an equations. We are all familiar with this dissipated energy, which is function of a stress amplitude and the strain amplitude, and delta here is a phase angle. The suffix O is given for an initial cycle and N is given for an nth cycle. So, with this equation, you can calculate the energy dissipation per unit volume per each cycle. So, this W gives you a energy dissipation per unit volume per each cycle. Now, calculate the energy dissipation, and if you plot a energy dissipation, as we already saw, energy dissipation for a strain control test, this is for a strain control test, decreases with number of cycles. So, energy dissipation for a strain control test decreases with the number of cycles. So, calculate this energy dissipation value and find the ratio called energy ratio. This method of post-processing approach was suggested by Rowe and Bulletin. So, find the energy ratio, which is nothing but the ratio of energy dissipation value at the initial cycle to the nth cycle, and multiply by n here. So, this energy dissipation ratio, when you look into the trend of energy ratio, you will see a energy dissipation trend exhibiting a two-stage slope. One is where the slope is very small, second is as the slope increases. So, this two-stage slope, the point of intercept of this two-stage slope is determined as a number of cycles to failure. So, this is the energy ratio method, and as we said already, Lissajous method in this. So, you have a Lissajous plot. If the Lissajous plot here at the initial cycle is perfectly ellipse, we assume that there is no damage in a material, and as the Lissajous plot deorient from the ellipse over as the loading cycle increases, the damage occurs slowly. Now, if you see at the extreme cycles of a loading, the Lissajous plot is not an elliptical shape. So, now comparing the regular ellipse with the stress strain plot, you can measure a extent of fitting using an R square value. So, now if you plot a R square value as a number of cycles, you will have a trend something like this. So, again this trend here, the point of change in slope is used in determining the fatigue point. So, this is again a hypothesis what we make. So, in the next method, we use the energy dissipation ratio for calculating the fatigue life. So, as we said already, in a strain control test, the dissipative energy decreases, and in the stress control test, the dissipative energy increases. So, now if you compare a dissipative energy between two cycles, between two consecutive cycles, either in a stress control test or a strain control test, compare a dissipative energy between your two consecutive cycles and take a ratio, you will get a plateau region something like this at the second range. So, this is a ratio of energy dissipation or ratio of dissipated energy change is calculated using this expression. So, in a you see in a strain control mode, M and N represents the number of cycles, previous cycle being more than a next consecutive cycles. So, N is greater than M in a strain control mode. So, we calculate the RDEC based on this value and plot it as a number of load cycles. You will see this RDEC curve to be a tub shaped. Now, you have three phases here, phase 1, phase 2, phase 3. So, the point where the phase 3 starts represents the damage in the bituminous mixture, and we take this as a fatigue life of a bituminous mixtures. So, we have seen a different post processing method of 4-point beam bending test now the next is we will see how to conduct the indirect tensile strength of bituminous mixture and what are the post processing. We will also discuss the post processing methods available, and finally we will relate all these laboratory test results to the mix design. Thank you.